All right, so I'm Olivier and I work at Ledger in the security lab, and I'm doing essentially research to see how chips are secure. And today I will present an attack that we performed on a secure memory. So I will start by introducing the context of this evaluation. I will show the setup that we used and how the circuit that we broke is supposed to be used. I will then present 3 different vulnerabilities that we found for this work. I will present a very small countermeasure that should be enough to prevent our attacks. And finally, in the last part of the presentation, I will talk about some challenge that the wallet manufacturer sent us, and in particular, we had some troubles in sample preparation. Okay, so we studied the Coldcard hardware wallet. This is a device which stores a private key called the seed. This is a private key used to sign all the transactions on the blockchain. And so if you manage to steal a user wallet and retrieve that secret, you are able to steal all the funds. So this is a very, very sensitive secret. In this device, the seed is split in 2 shares. The first share is inside the microcontroller, which is a STM32 device. So you may already know that it's not a very secure microcontroller. And the second share is inside the secure element, which is a ATECC device, whose revision depends on the hardware wallet revision. So if you want to get the full seed, you have to attack both circuits. We started this work a long time ago, and at the time we evaluated the ATECC 508A device, which was in the Coldcard wallet, and we found a single fault attack, which allowed us to retrieve the secret stored in the secure element. Following this, the circuit was considered not recommended for new designs anymore, and Coldcard migrated to the successor of this circuit, which was already available, which was the 608A. And so we had a look again, and we found that the vulnerability we identified was still present, but this time we had to do a double fault attack. So this is because the manufacturer of the secure element added a double check countermeasure. So they were maybe already aware of that kind of attacks. Following this, we reported our findings to both the hardware wallet manufacturer and Microchip. And 1 year later, Microchip patched the circuit and released the ATECC 608B, which will be the topic of this talk. So the circuit, as stated by Microchip, is GIL-I rated. This means it is supposed to resist to high attacker potential. So they probably sent the chip to a lab to have some security assessment, but still we found some vulnerabilities. So this is still a circuit in production. Here you can see a photo of our setup. So on the top right, you can see the circuit, which is soldered on its backside, and we decapped the package to gain access to the backside of the silicon. On the bottom right, the circuit is mounted on our scaffold board. This is a board which sends commands to the circuit, gets the responses. It also has a pulse and delay generators to trigger the lasers, and there is also an amplifier to measure the power trace of the circuit while it is running. And this kind of power trace gives valuable information to the attacker because we can try to infer what's going on. Everything is under a microscope, and the microscope has 2 purposes. The first purpose is it allows us to observe the internal layout of the circuit, so we can identify where are the interesting parts of the silicon. And the second purpose is to focus the laser beam to have a very, very thin laser beam. Like the laser spot we have is 1 or 2 micrometers wide, which allows to target a small bunch of transistors. So this is a very expensive equipment. It's more than 100K, so it's very, very expensive, and we don't need such precision for this work. And more recently, my colleague Michael Mouchou built a cheaper test bench, which there is no more microscope and there is no more camera. So the laser spot is bigger, but it's still enough for this work. If you want more information, there's a link where you can find on how to build this kind of setup. So it's cheaper, it's more like 10K instead of 100, so it's more accessible. We'll see that the success rate is lower with this setup currently, but maybe we can still improve it. Okay, now you can see a picture we've taken with a microscope of the silicon. And regarding all the revision of the circuit that we looked, we found that they all share the exact same hardware. We didn't see any optical difference, and so when Microchip release a security fix, they probably only update the ROM memory. There are a few interesting memories that we can identify. On the top right, there is a static RAM, which is used to store the firmware variables and also some buffers for the commands. On the middle, there is the ROM memory, which stores the firmware. So this is where the instructions executed by the CPU are fetched. And more importantly, on the top left, there is the EEPROM memory, which is 10 kilobits, and it stores all the user data, such as keys, and also the configuration of the chip. So you cannot read or write anywhere in the EEPROM as you want. There is actually some kind of file system defined by the firmware, and there are commands to read or write. And so I represented the organization as this. On the middle, there are 16 user data files, which usually stores private keys. So they are usually very small and they have fixed size. For instance, the first 8 slots have only 36 bytes. So this is very small, but still big enough to store a private key. On the right, there is a one-time programmable file. I won't go into details with this one. And on the left, there is the configuration file, whose purpose is to store some configuration of the circuit, and also defines all the access rules to all the files. So you can have public files, you can have private files, and you can define rules such as you need to authenticate to a file to be allowed to read another file. All the work we did was in black box approach. We don't have the source of a chip. We don't have the firmware, so we don't really know how it works internally. And so we had to do some reverse engineering to understand how it manages to protect the secrets. And so far, there are a few points here that are interesting to keep in mind. So first, the public files are stored in plain text, and there's no integrity protection. And this is okay because it's public. The configuration file is stored in plain text as well. It is always accessible. But there is an integrity mechanism. That is, when the chip is powered up, it will calculate the checksum of the configuration file and verify that it matches the expected value. So you have to note that this is only done at boot time, not during the execution of the circuit later. And finally, we found that private files, so the secrets, are stored encrypted with AES. And we suspect there is also an integrity mechanism. If you remember, for instance, the first 8 files were 36 bytes long, and when they are configured as private, you don't have access to the 4 last bytes. You can only read or write the first 32 bytes. And so we suspect that there is an integrity tag stored in the last 4 remaining bytes. In the case of Coldcard, there are 3 interesting files. The file number 9 is the seed. The file number 3 is a pin hash with some salt. And the file number 1 is a pairing secret. So this is a secret shared between the microcontroller and the secure element. When the microcontroller wants to access to the seed, it cannot read it in plain text. It has first to establish an encryption session key with the secure element. And so this is done by deriving the session key with some nonce numbers and the content of the secret pin file. Once the session key has been calculated, you can call the read command and the result is returned encrypted and the microcontroller can decrypt it using the session key. This might not be enough, so there's one more rule defined in the configuration, is that before being able to generate the session key, you have to authenticate and prove that you know the pairing secret. So those are the commands involved in the access, to access the files. So for the authentication, it is called the checkmark command. For the key derivation, it is the gendig command. Both of those commands involve also the nonce commands to exchange random numbers. This is to prevent some replay attacks, I think. And third, there is the read command, and in the case of a private file, you have to decrypt the response using the session key. Okay, so let's dig into the first vulnerability. So actually, the most straightforward attack path as an attacker should be to directly break the read command, and the goal would be to make the chip believe that the seed file is public and not secret. If you remember, the configuration is stored in the EEPROM memory, and so we can try to fault it at runtime. And actually, this worked very well with the first two revisions of the chip, the 508A and the 608A, with a single fault on the first one and a double fault on the second one. And so when we decided to investigate the new revision of the circuits, we, of course, had a look at the read command to see if we could break it again. You have to know that there is a serious weakness in this circuit, is that the EEPROM can be kind of manipulated. So if you illuminate the middle of the EEPROM with a laser, you can force any access to the value 0. And the position of the laser does not depend on what byte you are trying to fault. You just have to shoot anywhere in the middle and it works. And the success rate is very high, so this is a very powerful fault model. You can do the same if you shoot at the bottom decoder of the EEPROM memory, you will force the access to the value FF. So we had a look at the read command, and we found that Microchip indeed patched this command and added some countermeasures. So instead of having a double check, this time they added up to 8 security checks. That's a lot. I think they're kind of scary, maybe. And they also added some software jitter countermeasure. I'll show you what this means exactly. So here is a power trace during the execution of the read command in the previous revision of the circuit, the 608A. And there is like one security check which is performed here, and right after, if the check is passes, you can see the file access loop. So there is 8 turns in this loop, so each turn they are fetching 4 bytes. This is only half of the power trace, because the chip does this 2 times, so much later there's one more security check and one more EEPROM file access. If you repeat this command many times, you'll see that the security checks always happen at the same time. So it's easy as an attacker to configure your delays to inject the fault when the security check is supposed to happen. Now, regarding the new revision of a chip, we can do the same experiment, and what we found is that there are actually like those 4 security checks, and then the file access loop. And once again, this is only half of the power trace, so it does this 2 times, so it does up to 8 security checks in total. And if we repeat the command many times, you'll find that now the security checks are not happening at the same time anymore. So this is a real problem for the attacker, because you cannot predict when you have to shoot with a laser. And here I highlighted what the random delay looks like in the power trace. So it's very flat, and you can see that there are many of them during the different operations of the circuit. Okay, so because of the jitter, the success rate of an attack drops a lot. And with 8 faults, it should be almost impossible to do with fixed timings on the lasers. But as we saw, we can identify patterns in the power trace, and in particular, the random delays are very flat. And so we can use advanced techniques such as real-time resynchronization to try to inject the fault at the correct time. So this is on the right a board that we fabricated and we used to try to fault all the 8 faults. And actually, we managed to bypass all the 8 security checks using 8 faults. So this took a lot of work actually to tune the fault injection parameters, but we found that it worked because the power trace obtained during the attack was exactly the same as an allowed read command. However, the problem was that the return data was incorrect. We never managed to get the correct seed with this attack. We don't really know why, but we suspect that there may be one more countermeasure that they added. So if you remember, private files are encrypted. And so when the secure element wants to access it, it has to decrypt it. And we believe maybe the decryption key is derived from the configuration. And as we are faulting the configuration to make the chip believe the file is public, maybe we get an invalid decryption key, and so we just get garbage on the output. So from that, we were kind of disappointed, and we said, okay, very good job, microchip. The command is much more difficult to break now. Actually, we did not manage to break it really. But it's not over, and we wanted to actually try to understand why it didn't work. So we had to run more experiments with the chip. You have to try to inject faults, see what happens. And there's one particular thing which is interesting in that circuit, is that the memory for the instructions is separated from the memory for the user data. And so if you illuminate the EEPROM while the chip is working, you will only corrupt accesses to the EEPROM memory, and you won't corrupt the instructions which are fetched by the CPU. And so if you illuminate while the chip is not accessing the EEPROM, there's no effect. That means we can try to illuminate the circuit during the whole processing of the read command. And in theory, this should produce 3 different effects. First, it should bypass all the security checks. Secondly, it should disable file decryption, because the file is now considered as public by the secure element. And the third effect, which we would like to avoid, but in this case we kept it, is the content of the file should be replaced with all zeros. So this is what the power trace looks like during this experiment. You can see the effect of the laser pulse, which is very long, like I think it was 1 millisecond almost. And so the expected response should be all zeros, as I said. But when we tried that, we got that value. And so we were very, very surprised. You can see this is not just random value, it is reproducible, and from the shape, you know, it smells in a way. You know something bad happened. So what we found is that actually we discovered an internal security mechanism, is that they use some masking keys. This is how I decided to call that. So actually the files are not stored as is in the EEPROM memory. They are masked with some weird key. And the key is different from a file number to another, and it is derived from the file number, actually. We also found that the keys are different from a chip to another, so you cannot reuse the keys you found on the circuit into another one. And we managed to extract all the masking keys for all the user files to see what it looks like. So this is definitely a vulnerability. You'll understand why later, but it's not useful alone, actually. We also wanted to confirm our XOR masking hypothesis, so we ran another experiment. So instead, this time, instead of faulting to the value 0, we shooted at the bottom of the EEPROM to fault to the value FF. And what we obtained in the response was the exact complementary of the masking key. So it kind of confirms what we believed. Here you can see all the masking keys that we extracted for a given chip. You can see that the entropy is very low, and there are some patterns, like for instance the on the first 4 files, it always starts with a value 5. I don't know, then it's 777, 1111, 3333. So you may want to have a look and try to find out how it is derived from regarding the file number. It's interesting. And in our case, we will keep those 2 values. So the M1, which is a mask for the pairing secret file, and M3, which is the mask for the user pin hash file. So here I have a small video of how it works. So you can see on the left the circuit that is being attacked. We are running the read command many times in a loop. For the moment, the laser is still off. We can monitor the power trace for each experiment on the bottom. You'll find that actually the real power trace is a bit noisy. It's difficult to observe what's happening, so we can apply some low-pass filtering to see the patterns. And here it is. And you may have observed that the patterns are like dancing every time. This is because of a jitter countermeasure. And now we will turn on the laser during almost the whole duration of the read command. You can see the effect of a laser on the power trace. So this was done actually on the cheap equipment, so the success rate is not very high, so you have to repeat the experiment many times, and at some point it should work. And now you get an OK response from the secure element, and you have the masking key in the response. Okay, so we didn't manage to get the seed by faulting the read command, and so we decided to go to the other attack path, which is getting authenticated and enforcing a chosen session key. So this is the authentication command, and the goal is for the microcontroller to prove the knowledge of the pairing secret D. There are numbers, random numbers exchange, which is represented by the value R, and the value O is for other parameters which are public. So during the verification process, the secure element will fetch the secret. So it will read the EEPROM memory, which gives the value E. It will unmask it with the mask M1. And since this is a private file, it has to decrypt it using AES. This is what the power trace looks like during the checkmark command. So on the left, there is the EEPROM file access loop. On the middle, you can see the rounds of the AES decryption. So there are 2 blocks to decrypt. And on the right, this is the beginning of the hash calculation, which is very, very long. With a single long laser pulse, we managed to produce 2 effects. First, we could disable the file decryption, because the chip now believes the file is public. And secondly, we could replace the accessed content with all zeros. So there are actually 32 bytes faulted in that case. So the secret fetched by the secure element becomes the value M1, and then the challenge is much simpler and can be calculated by the attacker. And so we could get authenticated using this method. You have to notice that this attack is only possible because we extracted the masking key. So it's only possible because we found the vulnerability in the read command. So this is what it looks like. This time we are running the checkmark command. The laser is off, so we get a verify miscompare result in the response from the secure element. And so we turn on the laser during the EEPROM access, and you can immediately see that now the decryption of the AES decryption disappears because we flip the file to public. And we now have to wait that all 32 bytes to be faulted to make it work. So this can take some time, and here it is. So we get authenticated. Okay, now what we still have to do is to enforce a particular session key to go to the full process. This is how the session key is actually calculated, so it's quite similar, just the ordering of the different hashed values is different. And the attack is very similar. So we could one more time disable the file decryption and replace the content of a secret file with all zeros. So the session key calculated by the secure element becomes this value, and as an attacker, we can calculate and find the same session key. So once you have the session key, you can just call the read command, and this time you don't have to inject any fault. The read command will return the data encrypted with the session key, and you have to decrypt it. There is one particularity with this attack, is that if you failed to fault the gendig command, you will end up with a different session key than the one calculated by the secure element. And so when you will try to decrypt the content of the read command, you just get invalid data. And there's no error status code. So you don't really know if it worked or not. So you have to repeat the attack a lot of time until you find the same decrypted value twice. So this is a recap of the whole process for retrieving the seed. So first, you have to corrupt the read command twice to get the mask M1 and M3. The success rate is very good on the high-end equipment, and on the cheaper equipment, it's not that good, but it's still enough. Like we can do it in a few minutes. We are still improving that result. Then you have to hijack the checkmark command to get authenticated. This allows to execute the gendig command. And if you failed, you have to redo the checkmark command because the authentication is valid only for one call to the gendig command. And finally, you can call the read to get the secret. So we are still trying to authenticate in this example, and you'll see that when we get authenticated, we run the gendig, the read command, and we get the output decrypted. You'll see that every time we get a different value because the gendig command failed, and so we repeat the experiment a lot of times. So I accelerated the video a bit. It takes, on this cheap setup, it took, I think, half an hour to manage to break the device. And at some point, you'll see that we get the same decrypted value twice. Yeah, so here it is. So we can display all the different decrypted values what we got, and you'll see that we had a lot of them, like almost 200. And actually, only 2 of them are similar, and this is the correct seed that we extracted. At least the second share of the wallet. Okay. So we proposed a simple countermeasure to prevent this kind of attack. So you may understood that the main issue is that you can fault every access to the EEPROM memory and replace the content of the files with all zeros. And to solve that, what you can do is insert trap accesses in between the byte accessed. You have to do it randomly, so the attacker cannot predict which access he has to fault. And this way, the firmware should be able to detect the attack. The only drawback is that it will increase the processing time, but as you saw, the file access loop is very small compared to the whole duration of the command in general, so this is an acceptable countermeasure. Okay, so now the question we get is, okay, this is a quite complex attack. Is this realistic? Is this practical? And this is why the wallet manufacturer, Coldcard, sent us 3 devices already configured and asked us if we could try to break it to prove that we were able to do so. And it turns out that attacking real devices is not that easy, and I'll give some experimental feedback on what happened to us. So first, during our research, we used circuits in SOIC packages because it's simpler to prepare. And the real wallets have a much smaller form factor package, which is UDFN8. So it's more fragile, and you'll see why. In our first attempt, we tried to desolder this circuit, and some bad thing happened, is that a pad from the package broke, and it stick to the PCB. So maybe we did not desolder correctly, I don't know. We had to heat a lot because of the thermal pad, but still, we broke the circuit. So the silicon is actually not dead, but maybe you can try to restore the connection, but you need extra equipment, and we don't have this. So we considered the challenge as lost. Then usually when we prepare samples, we have to stick the packages on a machine, which will, with a drill, remove the thermal pad that you see. And so for this, we usually use double-sided adhesive tape. But with UDFN package, the area of the package is very small, and so the adhesive is not strong enough to hold the circuit in place. So what we did, actually, we used some 4 metal sheets on each side to block the circuit on the machine. We validated this process with many circuits, so we were quite confident that it would be okay. And when we tried on the real circuit, it broke in 2 parts. So this was the second attempt to break the challenge. So this is a result of excessive mechanical stress. We believe that the package broke at its weakest point. And the question was, why did it work with the testing samples and not with this one? And so the testing samples actually came from a reel. It has never been soldered. And so maybe the real experiment, we desoldered the chip, and so maybe the high temperature has weakened the plastic. So the main issue is that the package is too small and too fragile. And there is one simple solution, is to make a stronger package using epoxy resin. There is one drawback, is that you cannot do the attack within a day anymore. You have to wait for the resin to harden. So in the case, if you steal a wallet, maybe the owner will have more time to take back the funds before you do the attack. So for this, we designed a small mold that we 3D printed. So you can put the mold on a sheet of paper, you place the secure element on the middle, and then you can pour the resin inside. On the left, you can see the first attempt in doing this. So it's almost good, but you can still see some bubbles in the resin. This might not be a problem, but if there is a bubble close to a pad, maybe it's not very good. So we managed to remove the bubbles by putting the epoxy resin into a vacuum chamber, and this is the result on the right, which is much better. Here is an attempt to do the resining, and actually when you put in the vacuum chamber, there are a lot of bubbles, and it makes like kind of foam, and the epoxy resin goes out of the mold, and it spills everywhere. So it's not very good. It's easier actually to remove the bubbles before pouring it into the mold. And there are a lot of bubbles because actually the resin has 2 components, the resin and a hardener, and you have to mix it, and during the mixing operation, you basically introduce a lot of air into the mixture. Once the resin is hard, you can get the result on the left. You detach the sheet of paper, and there's still a thin layer of paper, which is glued to the sample. And you can use sandpaper to remove it gently, and you get the result on the right. You know you can stop when you see the color of the thermal pad turning to orange, which is the color of the copper. Then finally, we can use a 2mm drill to remove the backside lead frame, which gives the result on the left. And you can see the mirror-like square on the middle is the silicon that then you can shoot with a laser. And on the right, this is after soldering back the samples onto the daughter board. So finally, we managed to break the third challenge. We recovered the seed, and this was confirmed by the wallet manufacturer. So it was still a success for us, because the goal was to at least manage to successfully break one. And we believe that with more experience, you can do much better than this yield. So to sum it up, our fault injection attack on the secure element is very safe. Actually, we never lost a device because of the laser. The most tricky part is on the sample preparation. So you have to be sure that you won't get any trouble, especially if there is a lot of money inside the wallet. And if you remember, we have to break both devices. So we had a fault injection attack on the STM32L4. Which is very risky, so we trained for many months before being confident enough to do the attack. But for this circuit, the sample preparation is much easier, so this is good. Finally, I can say that we demonstrated that the attack is practical. There are cryptocurrencies hardware wallets can have a lot of money inside, and so we believe that this is a realistic threat to be considered, especially because we managed to reproduce it with a cheaper test bench. So all the vulnerabilities we presented were disclosed to Microchip and also CoinKite, which is a manufacturer of the wallet. And since this is a hardware issue in the silicon, it takes a lot of time to patch. So we granted a very long period of time for Microchip, more than 1 year, before they could release a new revision of the circuit. For the cold card wallet, they decided to add a secondary secure element, which is one of the deep cover from Maxim Integrated. And if you're interested, you can have a look at a recent presentation of Karim Abdelatif on how he managed to break it. And so now the secret is split in 3 shares in this wallet, and so it makes practical attacks much harder, I think, because you have to break 3 chips. We've seen that the security of the ATACC circuit family greatly improved over the years, so this is a very good thing. In a few years, the chip became easy to attack to very hard to attack. So it's good that Microchip took it very seriously and patched the flaws that we reported. But since they still use the same physical layout, the EEPROM is still vulnerable. And so maybe there are still commands which are vulnerable that should be investigated. This is very difficult actually to patch all the commands, I think. And maybe also they are limited by the size of the ROM memory. Maybe they cannot add a lot of countermeasures. But more recently, we found like 2 months ago, Microchip released a new revision of the circuit, the ATACC 608C. So we didn't have time to investigate yet. Maybe this will be future work. I don't know. Yeah, so I'm a bit earlier than I thought. So I think we have a few minutes for questions.
Thanks, Olivier. Let's give a round of applause. And we have about 5 minutes for questions. Here's the first one.
Hi, Olivier. Thanks for the great presentation. I especially like the part about the failures with the package decapping. My question is regarding the microcontroller, the STM32. I saw that there were a high risk of failures for fault injection there. Could you explain a bit more why that's the case?
Yeah. So actually, the attack we found, some other teams, I don't remember the names, found a similar attack. I think it was 1 year ago, when basically with EMF5 they break the erase command of the circuit. And so the attack is on the erase command, and as you may understand, if you fail, you erase the chip and lose all the data. So, it's easier to say, okay, I found the vulnerability on the erase command, but it takes a lot of time and a lot of work to make it reliable and be sure that you won't destroy the device, actually.
Thanks.
All right. There's a question here.
Thank you for the presentation. My question is the following about the epoxy resin. I was wondering if you've tried UV cured epoxy resin. It takes less than a minute.
That's a good question. Not yet. Maybe yes, resins that we use in 3D printers could work as well. I don't know. This is definitely something to try, especially if it helps in reducing the curing time. It will be very helpful, I guess.
Well, if you want to reduce the curing time, UV resin, it's a way to go. It's more expensive, but you need such a small quantity that is probably not appropriate.
Yeah, I guess price is not very important when you have such equipment. Oh, yeah.
Thanks. There's the third question here.
Hi, thank you for your presentation. I have a bunch of questions. First one, how long does it take you to do this identification step? And the corresponding question, how would you estimate the GIL rating of your attack?
So actually it took, I think, like 4 months of work to break the 608B. But this is not fair to say only 4 months, because actually we had a lot of experience in studying the previous revision of the chip. We understood a lot of things during the previous work, and so definitely it was a help to know how to break the secret. I don't know if we would be able to break it without finding the previous vulnerabilities. So this is something I would recommend when trying to break a circuit, is trying to look if there are previous versions of a circuit which may be less secure, and that would help you to understand and reverse engineer how it works, and then try to increase the difficulty with the most recent revisions. And regarding the GIL rating, I'm not very familiar with GIL rating, and I know it's always subject to a lot of discussions. So I don't know, honestly.
Thank you. Another question is about silicon preparation. You said that you removed a metal part, but did you polish silicon? Did you thin it out?
No, actually, we have enough power to shoot directly on what we have. Sometimes we can thin the silicon when you don't have enough power, but for this attack, it's not necessary. It's a bit limited. Maybe you can improve the success rate a lot if you thin down the silicon, but it's adding extra risk to the preparation.
Okay, and the last question from the same side.
Yeah, the neighbor. First, amazing talk. Second, at the beginning of the talk, you mentioned that injecting a fault would lead to zeros or ones being read, but I'm not sure to remember, how did you find this out?
So this is something we found in the previous studies. Actually, we tried to fault. The configuration file is always accessible. You can always read it. And we tried to fault while reading this to see the effect. And at some point we found that we could only fault bytes that were not zero. And so we understood the fault model this way. And much later we tried also to fault other public files to see the effect. So it's part of characterization work, which can take a long time. But once you find it, it's a very powerful fault model. Actually, it's a bit difficult to find because there is the masking countermeasure, there is the AES encryption, and so sometimes you try to fault a file and you get random faults and you don't know why. So, yeah.
Merci.
Okay. Thanks, Olivier. Let's give a round of applause.